It was maybe just a difference that I was not much listening to what others might say. Kind of, I could figure out things that it is something is important, and I felt always that it is important, and try to believe that it is doable, and not listen to those that said not so. It is like imagine something that I can have an RNA, and I have to tell you, I did not want to develop vaccine at all, and that was the reason I was looking for with colleague Drew Weissman, that how to make it non-immunogenic, because everybody thought that the immunogenic RNA is good for vaccine, but I want to use a therapeutic. And I could imagine like other big names like Steve Jobs that imagined that there is a device, and that will be your telephone, that will be your camera, that will be your all different device in one piece. And today we take it granted. I just imagine that there will be RNA we are taking out from our refrigerator and put on our wound. And because the advantage of the RNA is that taken up by the cells, and locally they will produce a protein which will be beneficial, which will be therapeutic. Otherwise, if you put the protein there and it will wash away from the blood, here is also, but it is continuously produced in locally, so there you have a gradient. And I imagine that it is doable, and it will be helpful for some kind of disease, like healing the skin. That was my first thought. And then later, when we realized that, not much protein is made from the RNA, thinking about what disease model could be, which a small amount of protein is beneficial. And finally, we ended up with treating anemia. And we come up with a messenger RNA coding for erythropoietin. And because for continuously the erythropoietin mRNA, which we delivered to the animal, were like 4 days, was continuously translated, we could see new red blood cells formed, and we could see the hematocrit increase. So it was the RNA translated to a protein, erythropoietin, which stimulates red blood cell production, and it was functional. The RNA translated to a protein was functional, and more red blood cells was made. And so we found at least one disease where the mRNA could be beneficial. And of course, I was working on this field where Drew Weissman tried to make a vaccine, and realizing when he used once this modified, nucleosine modified, which was non-immunogenic, that was many twists and turns. Turned out it was better vaccine, because the original RNA everybody was using is turned out toxic, especially in human, and they couldn't see as well in animals. So that was also one thing that Drew Weissman used human immune cells, and we could see that, the RNA, conventional RNA, is inducing immune response and inflammation, which was not good. I have to mention that sticking with a project is worse when you can see progress. So I could see progress. I could see that I could make the RNA better, more protein was made, and so that sticking with something and repeating just because we are believing and not making any progress is not a no-no. But I could see that it was better. And when I received the grant review, and they said that it was, was not good enough, and I read through the criticism, I always listen and try to, it made it better. So more preliminary data generated and more experiment I performed. And I didn't take it that, they did not understand me. It was just, not good enough. And I have to do better. That's how I concluded with all of these constructive criticism. So early on in high school, actually, I read this book written by Hans Scheie, who was coined the word stress. And it was a big effect on me. I had no religious upbringing, so that was a guide for me. And he said that the stress, how we perceive stress and bad stress can kill us. But he said that we need stress because excitement, anticipation, all of these positive things is, we need. Otherwise, we don't get up in the morning. We need stress, but we need positive stress. And he also said that you can learn to convert the negative one to positive. So positive stress is needed, and seeing everything like negativity, like losing a job, which happened to me several times, to see that one door closed, a new is open, and see that new opportunity. So not to, agonize on why I was terminated in my job, but rather just see that, okay, what I can do now. And so that was key, always to keep my spirit high, and which other people might take it as a blow to their career. I took it that, okay, now I can move to something, somewhere else and doing something, but sticking with the RNA because I could feel that it was exciting. And I learned in Hungary, when I started to work with RNA, I learned how to work with RNA, how to label it, how to isolate all of this enzymatic reaction, I can characterize it. So, and as years passed, I learned more and more about the RNA, and learn how in our cells we are making the RNA, and how we picked up different nucleotides, and we are building our RNA, and how it is changed, and how it translates to proteins. So I spent months and months just analyzing what is known about translation of the RNA, making from the RNA, making the protein. So I try to take the knowledge and further optimize my system. And so that's, I could see so many things I have to do, and nobody have done, but I thought that may be doable, just like Steve Jobs said that maybe it's doable, just we have to work on. And many, many things I feel that could be, we could solve the problem, but we are not focusing enough, or I don't know, some distraction. And that was the other thing, what Shaya said, that you shouldn't look at things you cannot change, meaning like, be angry with the reviewer. You cannot change. They are how they see things. And not to pay attention when in your workplace other people are promoted and working less and rewarded more. Don't pay attention. You cannot change that, he said. You have to focus on what you can change. And many times I actually said loudly that the bench is here. I am in America. This is where else, if not here, I can do if it is doable. So that's what focusing on what I can do and not worry about others I cannot change. Shaya, he was Hungarian, and that's why he lived in Canada, but his book was translated and in the 60s, and we could read and his book and about stress. And we wrote, in high school, we wrote him a letter, and he responded. And of course, you get this response. Everybody was reading the book because that's so exciting. And that's why, when I get letter from high school, I also try to respond, because I know that how impacted us. And for me, it was, this was very important to read and to figure out always, to see this positivity on everything. Even last time, just my colleague said, supposed to do something, and he said that he has not done. And because he didn't even order the material for it. And I could see one thing I can praise, that at least he was honest. He didn't say, I ordered and I'm waiting. So I praise for. And so he was enthusiastic and he started to do it. So you don't, I mean, this science, doing science is fun. It is, you solve problems. You don't sit in a crossword puzzle. Sometimes in science, you ask the question and you respond to it. So you, like in the crossword puzzle, you read the question, and then here you create the question. Oh, what should be? and then you check it out. And many things already known, and you know that it is known. You just have to find when you are looking for some problem to solve, and you think it must be known. And then you start to read, and somewhere you have to find somewhere in between the lines, and then you are in the middle of the night, you already 2 o'clock, 3 o'clock in the morning, you realize you didn't sleep, but you are so excited to find that it must be known. So that's also, you don't feel tiredness when you are doing this kind of work, what you like. And you have to work and do work which you like, because we spend our life with work. And if you like it, then you will be good at it, because that's what you want to always do it. I know that I did most of the time basic research. I did in Hungary. We did a small RNA molecule which we assumed that it has antiviral activity, and there were no antiviral compounds. And I'm talking about 1970s. And of course, even today, we know that it was not many antiviral compounds. And every time I was doing something, I always, that would be good. I could imagine that it will be as an antiviral compound. I was doing the RNA work, and we could manage to deliver RNA into the cell. The desired protein was made. And then we were thinking that where we could have used this, and imagine that bone marrow transplantation, and we could deliver an RNA coding for a protein, which would make the lifespan of those cells much longer by delivering telomerase mRNA, which code for the protein. And so every time when we could do something, we were thinking about what we can use this. And when we could deliver in the animal, then we could say, maybe it will work in human, or maybe for animals, for companion animal treatment, or farm animals would be beneficial, different disease to treatment, as a treatment. Because who is working in a field, they are the best who they can imagine that what it could be used. And when I talking about human treatment, I work with colleagues who were physicians. They see patient, operated, like in neurosurgery, I spent 17 years. And the colleague could say that how they could reach this area of blood vessels. And then we were thinking what RNA should be beneficial to deliver there to help a stroke patient, for example. And so always, working together with colleagues and figuring out what is their limit and what they can do and what I can do, and together maybe we can solve and treat different kind of diseases. In Hungary, when I started as a graduate student, my supervisor and everybody around me were organic chemists. They synthesized, and I was supposed to set up an antiviral assay and then to work together, all of us. And I explained to them what I can do, and I try to understand what they can do. So this way I always learn. And then together, of course, we could figure out things which otherwise, if we are not talking to each other, we wouldn't know the problem or the solution for it. So that's also exciting. And later, as I mentioned, I work with physicians. I work in cardiology, like a molecular biologist could be anybody, anything, because molecular level is same. So that I work with cardiology problem, intima thickening, when the blood vessel is narrowing down, and we try to figure out what to do, what should be beneficial to deliver to the blood vessels. It was a very simple life. We lived in an adobe house, and we had reed roof, and we had a sawdust oven, and we had one room which was heated, during the winter. And my mother cooked on it, and we were doing our homework, and my parents worked very hard and late hours. And so for Christmas, we get a little pot that we could go with our parents to get water to the middle of the street, where the people were chatting and kind of, it was the chat room that time, because you learned what's happening in the city. And it was sometimes a lot of people gathered there. They already had the water, but they still. So that was fun. And of course, we have no television or a refrigerator, but nobody around in our neighborhood had any of these things. So I didn't know that I'm missing. What was important is the love and this childhood which we could have, that we helped out always. We worked in the field and with animals, but everything was, play. And so we didn't have to worry about like some other people had, that they didn't have enough food to eat. And I did not have that. And we could go to school and we had clothes and our parents, I have an older sister and she was very good student and always, set up the bar for me that I had to be also good. They expected me to be good if she was good. He was butcher, and he worked in a butcher shop first, and he also went to, homes that during the winter they had usually one pig, and they had to be processed because the people didn't have refrigerators, so mostly they smoked the meat to keep it, and they had one pig for the meat for the whole year, and so he processed. And he also in the war, like 4 years, he was cooking for hundreds of people. So he also went in the small town when somebody had a wedding, then he cooked there for many people. And so he was very well loved in the city, and he worked very hard. He didn't have the opportunity to get formal education. So he had 6 elementary and my mom had 8 elementary, but my father, they were very intelligent people. So my father was playing on violin and different instruments, and he was in the butcher shop. He could multiply 2-digit number. And I was, when we had the calculator, I already later, I helped him, by the time I punched in, he said, oh, the customer already left. So he was very kind, and he was always so enthusiastic. He was whistling and singing, and yes, so it was very, very happy life we had. And he knew so many things about history and things, although he didn't have too much time to go to school because he had to work. And that was also my mom. She was, my mom passed away 3 years ago, but she had laptop. She was looking up everything on the internet, and she could watch TV and set it up, the DVD, to record in the other channel. I didn't even know what to push in, but so she was also very talented, technically. Science is around us, science, because I was watching how the chicken coming out from the eggs, because we had chickens around the house, and so that these were all interesting. We put the seed in the soil, and as a children with my sister, we always had one part of the garden that we could put a seed there and watch how they are coming out. And we had birds and animals around us, and that's all everybody's interested. And, the stork is coming back and thinking that how they could come back here. And of course, different level, as you are a child, you are wondering all of these things. And in the school, we had very good teachers. So the chemistry teacher, she just finished school at that time, and she came and we did crystals. So we oversaturated solution and put a thread in it. And then we were just so happy to see a crystal. And I remember that even I was in the United States, I was already, 40, 50 years old. And when I could see a crystal sometimes form in the bottom of the bottle, I always stand and then I looked at how beautiful the crystals are. So, the teachers are very critical too. maintain curiosity and just help the child to think. So that in high school also, my teacher, who actually wrote the letter together to share, he always, when we discuss a topic, it was never closed. It was like, what do you think? Like we talk about like Lombroso, who was an Italian physician, realizing that in the prison, some characteristic those inmates had, and then he was thinking that maybe they born to be, they are born like that, and that's why they are criminals. And we just discussed this in high school, and then in 2010, the new chairman at University of Pennsylvania, the criminology, I could see he's talking about the lecture was advertised for about Lombroso. Oh my God! I learned about this when I was high school, and it turned out that some damage, some kind of injury happened to the mother on a certain period of time when empathy is developing in the frontal lobe, and that's why maybe this is what happened. Now that no better understanding of the biology. But what I'm saying is that something happens, you learn something, and early on in high school, let's say, or elementary school, and then you keep seeing things, and then you learning and building on that. So in elementary school, there were this, even 7th grade, I was third in the country. There is 19 countries in Hungary, and then in the 8th grade, I was in third best in the country. There was a whole week competition in Budapest, and it is also interesting because the small town Kisújszálás, where I grew up, it was 150 kilometers from Budapest, and my father put me on the train, and even I had to babysit another 2 years younger person who was also from my school, but for different topics. He was also competing in Budapest. And then they are waiting we get the letter that they are waiting for you in Budapest. So, you put a child 14 years old and 12 years old, and then, somebody will pick you up. And, my father learned that I made it when I returned 1 week later, that, okay, I made it, and I get third place. Oh, he was so happy. No iPhone, no we didn't have any telephone. And of course, there also you could see that some other kids maybe were parents had cars, and, but you have, that's fine, it was okay. And so I love plants, and a lot of question was at that time about plants, and then I was good at yeah. So of course, we learn in maybe in grade school. Sometimes we learn about messenger RNA, and at the university we learn. I mean, I was still studying when we learned that there are introns in it. So we learned a lot interesting thing about messenger RNA. And when I was 78, I started my PhD, and my supervisor Jenő Thomas. Actually, because I told you everybody was organic chemist around me, he synthesized a CAP analog in the 75, and he sent it to Aaron Shatkin to the United States because he discovered that there is strange structure at the 5' end of the RNA, and he needed reference material, what it could be. And so somebody had to synthesize, and it was my supervisor. So when I started in 1978, I already knew about the cap structure of the RNA, but we couldn't synthesize RNA at that time. We could not have the enzyme. It came on 1984, 85, when Harvard scientists reported that high-fidelity RNA polymerase from phage can be used to make mRNA, and that messenger RNA was functional, translated to a functional protein. So that is started in the second part of the 80s. Actually, that was a revolution. If you were on the field, every time you would just amazed that the PCR came. I mean, 1989 was Taq polymerase, the enzyme which is used. It was the molecule of the year in Science magazine, and so people started to could purchase PCR machine, and people, when they created some kind of little tools like delivery tools like lipofectin, which have to deliver the RNA inside the cells, they published, and in the same year you already could purchase. So immediately was commercialized, and that was also very helpful. So that, and also the RNA isolation. So if you had a cell which expressed a protein you were interested, and you could isolate the RNA, you could make a clone it, you could amplify, and you could make a template for the messenger RNA production. You could make the messenger RNA in 2-3 hours. You put on the cell, 15 minutes later, you could see and analyze the protein of interest. It was just unbelievable. You could do everything, and you didn't need an expensive machine or something, nothing. You were just sitting at the bench and the little pipette you are using, and that was it. Yes, so messenger RNA was discovered 60 years ago. In 1961, they described, and they couldn't find for a long time because they tried to isolate the RNA from cells, bacteria cells, but it was so labile. So the 2 papers which published in Nature, actually both has the title unstable. So why people were looking for this RNA? They knew that there must be something because they knew that in the nuclei we have the chromosome. In all of our cells we have the chromosome, the same chromosome. Yeah. But, we have hair cells, we have, skin cells, different kind of cells are different in our body. There are muscle cells. And of course, they are making different protein. But so from the chromosome, only different part of genes are made to something. And that was the RNA. And these were transcribing inside the nuclei, and it will come out from where the protein synthesis is taking place. And then the protein is made, and this RNA degrades. In the bacteria, as already translating and making, already degrading in 2-3 minutes, RNA is gone. In mammalian cells, in human, it is longer, but again, it is transient. And then if more protein is needed, more RNA is made and translate. So it is a messenger, which is the name says, carrying message from the chromosome to the protein synthesis place, to the cell where it is, there are ribosome, that's the protein machinery, and the protein is made. And so this RNA carries all of the information necessary for the protein to be produced. And the protein, it will have, when it is producing, it has the information in the start to make the protein, is where it should go out, should go to other part of the cell where it has to be located. And so it is, when you make a protein from outside, somewhere in a tube, and you just put on the cell, even if you introduce to the cell, the protein would enter and I wouldn't know where to go, because during the synthesis, where the synthesis occurring, there is where the reading and introduction to the information where it should go happening. So this is why this RNA therapy is, potential is so great, because you can deliver an RNA inside the cell, the protein is made inside the cell, and then it will know where to go. It might have to go to the nucleus, it had to go to mitochondria, different compartment of the cell, and that's the beauty of it. I mean, I worked with short RNA in the 70s because I couldn't make messenger RNA. I did isolated only, but I could not synthesize for desire. And because we did work with this shorter RNA, which had this antiviral activity, my thesis was to deliver inside the cell. And then it was problematic how we could put a negative, because the RNA is negatively charged, and to put to the cell, which surface is also negatively charged, so it won't go in. So then I tested out all kind of procedures that calcium phosphate co-precipitation was the name one. One other was I had to give a osmotic shock to the cell, and then it would like suck it up, this RNA. And but it was a short RNA, and it did work, but it couldn't use in a human body. It was just cultured cells. You could do it because they survive and they produce protein. But what was interesting is that prior to my PhD thesis work, as an undergraduate, I worked in the lipid team. And we analyzed lipids in fish and fed with different material. But we had also a team at biochemistry who they wanted to have a phospholipid to generate liposome because they want to deliver different things into the cell. And Eva Kondorosi and Ernő Duda was the team leaders. And so I was interested what they are doing. They were published already in 1980 that put the whole nuclei in this liposome and delivered in another cell. So now the other cell had two nuclei. And so here they wanted to deliver DNA and a plasmid DNA, which code for a certain protein. And so I participated in the project, isolated phospholipids, and we formed liposomes. And we already followed studies published in 78, published in Nature. So we are in the early 80s. And we did a plasmid. We put a lipid bilayer around it. They call it liposomes. And we put on the mammalian cells, and they picked it up. The DNA went to the nuclei, and the RNA were made, and the protein was produced, and we could detect the protein. So this was in my mind always when I could see some new progress was made for delivery material. So it is also very important that to start, even as an undergraduate student, just get exposed to some science, and then you are thinking about how it is. And this we generated RNA coding for urokinase receptor, and that was important to not to let the blood clot inside the blood vessel. So that has a role in it, and so that we just could make this. I made the mRNA working with Elliot Barnathan, who was a cardiologist, and we delivered to the cell. And this receptor had to be very decorated with sugars and had to be processed to be functional. And we delivered the RNA, and voila, inside the cell knew what to do, how to formulate, how to decorate, and we could see that this receptor was functional. We knew at that point, and it was in mid 1990s, like 95, 6, we did this experiment. We knew that the RNA would be good for something. That's what we said. And I remember it was about the same time before Christmas. We were standing there in this gamma counter because the ligand for this receptor was labeled with iodine, and then we want to see that could it bind, could it functional, this receptor, which we encoded by the RNA, and if it could bind, then we could see the radioactive material, and measuring this gamma counter, they call it. And then we stand there and we could see that, oh my God, we get high numbers, it could bind, and it was like all of this joy. I remember exactly how we stand there, and one colleague, Alice Kuo, Elliot Barnathan, and me, 3 of us, we were watching. We did this experiment together, and of course I moved on to neurosurgery, and we did more and more experiment. I did not realize that the RNA is inflammatory. It's not until I met Drew Weissman, started to work together, and in 2000, we realized that the RNA, what I was making, all these 10 years I was working in, that caused inflammation in human cells. And that was the reason, I said, I wanted to use for therapy, for stroke, for blood clot inhibition and whatnot. And it is all for nothing, because this is a useless, why? And then the question what we ask with Drew, why it is? In our cells we have RNA, why? I think that the RNA I am making is very similar to what is inside the cell. Is it because it's coming from outside and it sees our immune system as an invader, which turned out like that? And then there was the question, can we at all do anything and make it non-immunogenic? Because we didn't know that. And so that's what we started to work on with Drew Weissman, and did a lot of studies and many, many things that as a scientist, we don't know that, is it doable or not? I was working already 10 years at Penn. Actually, I was working at cardiology, which was Department of Medicine, but I moved to neurosurgery. But I still keep coming back to my friends and using also the Xerox machine, because I knew the password there. And then I've seen this new guy there, and so I introduced myself that I am working here, and he said that he just arrived, and he told me that he was working at an NIH, and he wants to develop a HIV vaccine, and he worked with Tony Fauci. Didn't ring a bell because I was not in that field, and so I didn't know who was doing vaccine research, and Drew was saying that he wanted to do vaccines and try different things, and I like to brag, and I brag about that. Oh, I make RNA, I can make RNA, and if you want, I can make it for you. And it was not by accident. By that time, maybe he was the 30th person I was offering to make RNA, because I gave other people, and one or two person, used it and published it, and I was also part of it. But most of the people, I just offering, I can do. They said, yeah, because I was like pushing it, and maybe probably still in their freezer, never used. But some people tried and didn't work out, and they told me so. But it was different with Drew, because he tested out immediately, and I made a HIV-specific protein coding RNA, and he gave me the gene, and I cloned into the right cassette and made RNA, and he was so happy that this works. So all of this immunological marker went up. Perfect vaccine, so much protein was made, and he was very enthusiastic about it. He said, all of these inflammatory markers. I said, that's not good for me. I don't want inflammation. I injected into the brain, maybe that is also, I did not see any effect that the RNA is not good, which I was doing. And I could see only when Drew tested out on immune cells, human immune cells. And then he added RNA, and these human immune cells made a lot of inflammatory molecules. And that was, I was worried. And today we know also that the human is much more sensitive to conventional RNA than the animals. So I did not see on animals the effect. One question was that why it is inflammatory, and that's we identified that it was uridine in the RNA actually. At that point, first we did not know. We just tried to understand. Okay, first we try to understand why it is inflammatory, because it's coming from outside. So those RNA, which is inside the cell, is not inflammatory. So what we decided that we isolate those RNA, which is inside the cell, isolate, and now try to put on the immune cells, human immune cells from outside. Is it is it inflammatory now? You understand? So it mimicking like you have an injury when you are just damaging your own cells. And we imagine that things are coming out from the dead cells and immune cells are reacting for that. And this is really what happened. So the human immune cells reacted and they did the inflammatory molecules. What was surprising is that tRNA, transfer RNA, did not induce any inflammatory molecules. And knowing that the tRNA has the most modified nucleosides in it, we were thinking that could it be that the modification of the nucleosides is making the RNA non-immunogenic? We have to try that. So we just have to make RNA with modified nucleosides. But how? Nobody ever done that. So figuring out how our body is doing, we are making from 4 basic nucleotides, our RNA, and then different enzymes will modify it. And more than 100 modification is known in the RNA, different nucleosides. But the enzymes, even the enzymes is not known. Not that you can buy one, purchase or order, and then you can just change it, the RNA. Okay, so we cannot do this way. So then we have to maybe purchase nucleotides which already modified and try to incorporate. So we looked at the literature. There were just one was published in 2003. Sousa, he tried, but just short RNA could be made. So we thought that we have to try and order different modified nucleotides and those which other people never tried. And we found that, we can make it. We can make a whole long RNA. Now the question was whether we can translate it. Because for either for vaccine or either for therapeutic protein coding RNA, we need translation. We need RNA to be made to a protein. And then with all of these studies, what we have done with the modification, we found that uridine had to be modified. And when uridine was modified any different way, we found that RNA was not immunogenic. So the nature created RNA the way that uridine, if it is uridine in it, this is one of the 4 basic nucleotide nucleoside in it, then it is immunogenic. But when you modify it, not. Now today we understand. There were toll-like receptor 8. There is a one receptor human has. Actually, mouse do not have that. And this is in the endosome of the immune cells. And when they pick up samples, which is RNA, and they degrade, the uridine, just the nucleoside itself, can activate this receptor. And when it is activated, you get inflammatory molecules. So today we understand the mechanism, but at that time we didn't know. It was very empirical. And but we understand that if we modify it, and we could make these nucleoside modified RNA by ordering the nucleotides. Today everybody knows this is how to do it, but at that time nobody knew it. And then we made, and that was it. And of course, again, we realized that we had to purify it. And again, nobody ever described how to purify. So we spent like 2-3 years figuring out how to purify. And one New Year's Eve, I remember I was in the lab because I had another idea. And then New Year's Day, I went back to the lab because double check something that maybe this way can do it. And you know, it couldn't be, but I was very happy. I told my husband, nobody was there. I could park right on the door. Nobody was working on New Year's Day. So it was, and working, and finally actually Drew solved this problem with the HPLC, come up with the column that we could purify the RNA, and we could make an RNA absolutely non-immunogenic. And so we knew that it would be good for therapy. So the publication came out, the paper came out, and then Drew, who is always so reserving and never says, he said, watch out, they were calling us, watch out, there will be, you know, telephone will be ringing, people want to use this. And of course, nobody called. And because I was always like bubbling, oh, da, 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 but Drew was not. But at that point, he was so optimistic that there would be a great interest for that. But did not happen. But of course, we could see that there are more things we have to do. And so we just keep working. We were not watching the telephone. So because I could see how we improved the RNA. We could make non-immunogenic. We purified it so it was not activating anything which would be detrimental. And so it was. We tested out in animals, first in mice, and we could see it's great. It was made functional protein. That was the anemia project. And we also tested out on monkeys. I, drove up to Washington, D.C., 3 o'clock in the morning from Philadelphia for, delivering to the monkeys the injection. Of course, not I injected, but I had to make the RNA complex. And seeing that they also made erythropoietin, and it would be expected that it would work in human as well. And so it was a great excitement. And then it was how we, from this project, we moved to the vaccine, was that one of the colleagues came actually from Hungary, Norbert Pardy. His grandfather and my father work in the same butcher shop in the small town. And I knew him, and he came to work with us, with Drew and with me. And then he was who started to formulate what kind of formulation we need for the RNA. And Drew contacted with people in Vancouver who were doing a lipid nanoparticle. Prior to that, we tested out many different formulations, tried to see that what would be the best to deliver the RNA in animal setting. And then they made this lipid nanoparticle, which is not the liposome I was trying, or what we were experimenting in the 70s, but it was a different kind of particle. And Norbert and he tested out, and it found that it was so powerful, so much protein was made, and so we thought that this will be very good for therapy and other things. And what happened is that when Drew and Norbert injected RNA coded for viral protein, they found it was an excellent vaccine. And at that point, everybody was asking, where is the adjuvant? What is the stimulant? Because, if you inject the foreign protein, immune system is not responding. You need something to stimulate, to make make the immune system to recognize that protein is dangerous. Please respond, make a cellular and antibody response against. And today we know that one component in the lipid nanoparticle is the adjuvant, which is activate. The RNA is not activating anything, seems like. It is non-immunogenic. And the lipid nanoparticle contains one component which stimulates the immune system. And this stimulant is very good to generate high level of antibody. Whereas if you leave the RNA as is, non-modified, it induces cytokines and stimulant, which makes the very low level of antibody. It was 2012, 2013 when started to make this lipid nanoparticle. It came from the small interfering mRNA, small interfering RNA field, siRNA field. They did the lipid nanoparticle, and there were companies in Vancouver. One was Tecmira, and the other was Acuitas, and they were working on this small RNA, and this and they needed just a system to work with the long RNA, because the messenger RNA is a long RNA. There are thousands of nucleotides in it. And they did about 2012. And 2013, when Norbert and Drew Weissman and Norbert Pardy were doing these experiments. 2015, they published first that it was how good this lipid nanoparticle with the nucleoside modified RNA. And 2017 was the first paper. Norbert was the first author. It published in Nature and showing that Zika viral, so generating a vaccine against the Zika virus. And this was the first time that this same formulation actually, which was finally get into the Pfizer vaccine, and the same formulation and messenger RNA, same composition, but it was coded for Zika viral specific protein. That demonstrated that it is very, very good vaccine. Why it was good? Because the same small amount which was good for a mouse, it was good for a monkey. You didn't need it to scale up. Those people who tried to make a DNA vaccine before, the major problem was that it worked very well in mice. But when it had to be larger animals, unproportionally more material had to be injected, but not in this case. Yes, so so again, in 2013, I lost my laboratory at Penn, and was asked to move somewhere else, and I didn't want. And this is one, coming the push, and also I could see that Moderna was already in the summer, in the spring 2013, they got $240 million from AstraZeneca, and I felt that the RNA is moving now to the clinic. It is moving. The nucleoside modified RNA will be in the clinic. The conventional RNA, the non-modified one, already entered in the much earlier, in the 2000 was CureVac was formed, and the first mRNA company actually in 1997 it was Merix. It was a spin-out company from Duke University. That was the first they used messenger RNA, but they used ex vivo added to human dendritic cells. But it went all the way to phase 3 trial. But injecting RNA and using for cancer vaccine started 2000 in CureVac, a company in Tübingen, and then 2003 they started human trial. So the RNA was in human trial, but not the nucleoside modified one. And these were mostly cancer, although CureVac also used for rabies. They made a vaccine, although it did not work very well, but that was attempt to make infectious disease vaccine with RNA. And then I gave a lecture on BioNTech, and I get an offer that stay there. And my only request was I want to work on nucleoside modified RNA. And Ugur Sahin said that, yes, I can work on it. Right now, and even that time, my responsibility was nothing to do with vaccine. I was to develop messenger RNA for therapy. And actually, the first project was, which we have done together with Sanofi, and those messenger RNA were coding for, sorry. So my first project was to make messenger RNA coding for 4 different cytokines, and we injected these mRNA coding for these cytokines into the tumor. And in animal, it worked very well. It eliminated also remotely located tumors, metastatic tumors in animals, and this entered to the human trial. And so next year we will learn that how it it performing, eliminating remotely located tumors. So that was my first project. And then we worked also other projects, but everything was, and I was responsible for therapeutic protein coding mRNA. And that was my main interest. It is just when in 2018, Pfizer approached us that they are interested to have mRNA-based vaccine against influenza, that I also started to participate on that project. And the modified nucleoside containing RNA, which was my main interest, and working with for other application as well. So that's what I focused on. But we had also replicative RNA and other type of conventional RNA, which we use in cancer vaccines. So we were not decided that time that which kind of mRNA will be in that vaccine. I was in Hungary and I was reading about, it was maybe in the beginning of February in 2020. And I thought that it will not come here because prior coronaviruses also, were locally spread, and then it was just disappeared. I was not thinking about that, but luckily our CEO, Ugur Sahin, and Moderna CEO, Stefan Bancel, they thought that they have to act. And that was the same Albert Bourla at Pfizer. He thought also that we have to act because maybe that will be a pandemic. And so thanks to these leaders, they moved quickly, and all of these vaccine for other diseases already were ready, both at Moderna, BioNTech, Pfizer, already everything was done. It is just changing the nucleotides order, that was what had to be done. The optimization, my team, I have a 7-member team, and they are very professional, well-experienced scientists, and we did a lot of improvements, screening things. So I started in 2013, and with a colleague, actually, Hiromi Muramatsu. He also left the family behind, and we went together from Penn to Germany, and we decided that no matter what, this modified RNA will get somehow to the patient. Because many times when we did the experiment and we get a good result, we just looked through the window and we could see the hospital. And we was thinking how we could get this to there. And one day I told him probably we had to take it. and he said that he will help me. And so he was a postdoc, and then we went and started everything. We start to screen formulation, and different companies who had some kind of formulation, we send RNA and start to screen. In 2014, we already identified Acuitas, a company who made this lipid nanoparticle. Eventually, it is in the Pfizer vaccine. Pfizer-BioNTech vaccine has Acuitas formulation. We found in 2014, when with Hiromi and my team were screening different kind of formulation to different companies, we screened. And also we did the optimization of the RNA, because there is a coding sequence, and there is untranslated regions, which is very critical. We already did with our team, we optimized this and found that if we use this so-called cassette, we get very high level of protein. So only the coding sequence. So coding sequence could be antibody coding, mRNA, or other things. That's what we have to change. And then we did also a very good improvement with this 5', the cap structure. Because previously we used enzymes to add the cap structure, and it was quite labor intense. And then and a company who approached us, and Trialing from San Diego, who developed a very interesting Cap1 structure, which improved the translation tremendously. And they did also a lot of different analogs. Each of them, we incorporated screen, and we identified this is the best. And so this is the process we went through for years. And then we identified, no matter what, this is the best construct. And then you just have to switch in the middle of that, because everything is done in DNA level. The template, which supply for the RNA production. So we did the old cloning for the this DNA level, and then we said, this is the best construct. No matter what, all project can ongoing. And so you just take and then put in the middle influenza coding sequence, or put some other therapeutic protein coding sequence, and those sequences you just can order. Okay, so 20 years ago, you couldn't order. That was, two German company actually started that you could order from them the sequence. Of course, people could suspect that people were infected and could survive, and so that there were, immune response, and so you could suspect that there would be, you could vaccinate, but of course, not all of the virus is easy to make vaccine against, and like for the HIV, turned out that those people who survived or infected but then survived, actually they have different genetic making, the CCR5 receptor was missing. You just cannot deliver it, it will be protective if I would take out the CCR5 receptor. So nobody knew until you test it out. So you had to make the phase 1 trial and the phase 1/2 trial, and then try to do different concentration of the RNA delivered and see that whether patient had response. So they measure the antibody response. And then when you had the phase 3 trial, then, not patient because they were not sick. So they were just individual volunteers. When they had some kind of symptoms, they went to, and then they reported, then they tested out whether they are infected with the COVID or not. And then they could see the big difference that those who get the real RNA vaccine, because the other get the placebo vaccine, those get infected, and those who get the real vaccine, they were not infected, or they were not sick, because they didn't measure infection that time. They measured just symptoms. They did not have symptoms. So it was November 8th, my daughter's birthday, and we celebrated with my husband, actually. It was a Sunday evening, and then the telephone rang, and Ugur, he called me because I was in home office in the United States, and other time he also called me up and told me when we had some news, and he asked me that, is there anybody else in the room? And I said, my husband is here, and he said, okay. And then I walk in the other room and I said, nobody's here. And he told me that how well the vaccine worked. And because already at that point, with Drew Weissman and Norbert Pardy, was tested out for HIV, for influenza, the same nucleoside modified RNA with the same formulation. And in monkeys and different animal models, and always it works so well. I expected. So that's what I told my husband. Oh, the vaccine works. I thought so, but maybe I did not have enough information that. But so other people were surprised very much that how effective it is. But based on all of these information, as well as seeing the phase 1/2 result, because we already knew that how high level of antibody was produced, that cellular immunity was produced, kind of expected that it would be very effective. Yes, I like chocolate, actually. And there is a chocolate-covered peanut, which called Goobers. And actually, it is made in Philadelphia 100 years ago. I didn't eat that one, which was made 100 years ago. That was the fresh one, but definitely that was my favorite always. But it was just like this movie theater box, and that's usually I actually gave when I went back to Germany to my colleagues. I always gave them these Goobers in this movie theater box, and although they had Milka, but everybody loved that too. And so I told my husband that I will eat the whole thing. So, of course, we heard the news that now then actually in the UK, they started in the beginning of December, they already injected the BioNTech Pfizer vaccine to human, and which is out of the trial. Now it was started the real life injection. And then I had a call that at University of Pennsylvania, they want to do it together, that with Drew Weissman and me will get this vaccine together. And so I was very excited, and which was the first time I experienced this, that we were going to this room, they set it up, camera and everything, action, and the other room already the healthcare workers get their vaccine, and they were lining up in every 6 feet in the hallway all the way, and then inside the neighboring room they were injecting, and the chairman, we walked together, and he said, the people that here are coming, the people who invented this vaccine, and they cheered and they clapped, and that was unbelievable. All of this emotion came. I felt the first time. I know that, and always that so many people contributed to it. I just mentioned all of the visionary leaders who realized that we have to act quickly. But all of these people who, from the day when 1960, I just told you, 1961, discovering the RNA, and everybody who figured out that how to make the RNA, how to deliver the people, everybody contributed. And so I always feel that way, that, I am one of the person, and I am so happy that I am one of them, that who did contributed. And for me, the recognition was never important, that recognized me. For me, it was enough that I know that I did. So many times I told my daughter that, oh, this rowing is so similar what I am doing, because, in rowing, they are going backwards and not seeing where is the finish line. And I told my daughter, this is, I'm doing. I don't know. I just hope that there is a finish line. But at least, you have the cocks in there, and you know that you are going to the right direction. I don't even know that I'm going to the right direction. But I am just pulling so hard, just like the rowers. And also when, she got 2 gold medals when it was in the women 8. So there are, 8 women, and they are pulling, and there is no star in a boat. Everybody had to pull in the same very synchronized manner. And so this is the same in working in the company, that we all had to pull together and doing our best. And there is no star there. Everybody is working very hard and doing their best, whatever is their specialty. And we are, in science, really, we don't know how far the finish line. We just hope that maybe we make it, or maybe, our discovery will help somebody else and taking to the next level. And one day somebody will be helped, because that's what all scientists want. They want that they are doing something and somebody will be helped. This is, for many scientists, this is what driving them. There's nobody starts to do science. Okay, I want to get certain award. That's what I want to be a scientist. Because for 40 years, day after day doing it, you won't be able to. You have to, and also the joy, what you can have. It is not the celebrity and the spotlight. If you like the spotlight, you should be an actor or actress, because then you can be every day in the spotlight. But working in a laboratory, you have to enjoy coming up with solution, seeing the problem, solving it, and this is fun. Yes, of course, it is unbelievable that it turned out that this modified nucleosides is so critical for the 2 vaccines that actually was approved. And you couldn't imagine that it will have such an impact, because, as I mentioned, that we are dreaming about to have at least one person. And that's what actually I stay in Germany, because at the beginning, I stayed there because I knew that BioNTech had already RNA in the clinical trials. So I said, modified RNA will be easier to get there. And then when we had finally in the trial with Sanofi for this intratumoral injection mRNA started, I said, okay, I just want to see one person is injected. And then it was injected, I said, oh, I want one person to see at least benefiting with all of this work. And then finally, 8 years later, I'm still there because always a new goal was there. And so I am, again, happy that, this vaccine is effective and it is safe. And what was for me is tantalizing is that previously all of the criticism was that it degrades so quickly. And now that people are saying, oh, it will stay there and it is a problem. Oh my God, for 40 years, I keep saying that, it still had enough time the protein is produced. And it is, all of the worry was about stability, and that people worried about it degrades so quickly. Now people start to worry about that it's not degrading so quickly. It degrades quite quickly. It is just enough time the protein is produced, and then the protein activates the immune system together with this element of the lipid nanoparticle, which activates, and the protein is also everything disappearing. Yes, I thought that the limitation will be that there is not enough vaccine. And it turned out that the people willingness to take the vaccine. And, they say that the viruses love democracy when people can do whatever they want. And they, but I also thought about that as a scientist, we have not done enough to explain what the molecular biologist is doing. I'm saying, we cut the genes in, put in. They don't know how. Do we have a scissor or we did not educated the public about that, what a scientist is doing, what a today scientist is doing. We are not looking at the microscope to see the RNA. It is very different, but we have not done our part. So from my part and you also, together, we have to do a better job. Because I believe that a lot of people genuinely want to understand, but they all of a sudden not just learning about mRNA, immune system, antigen, antibody, the people are just overwhelmed. And they don't understand how we understand today how the immune system is working. And it is because we did not educate it. And also I realized that the people were not interested, or we were not doing the job. Like if you go to the street and ask the people, can you tell a name of a scientist? Probably they would say Einstein or somebody. But you ask somebody who's still alive, they won't know. They know the name of the celebrities, and the people who created the medicine they are taking every day, and their own life is dependent. They never ask, who did this? Who did these pills? Who discovered? They don't ask this question. Maybe we should, tell them that, look, who discovered, the awardees, for example, James Allison. We wouldn't have, feedback inhibitors without him. I mean, this is evolution. The virus evolves, and then if there are enough subjects, they can enter it, and they will do and get more contagious variants, and this is I think it is natural that it will have that certain mutation. They cannot afford. We are lucky because the virus cannot afford all of the mutation, because they still had to have tools to enter, and when they are entered, they had to replicate. So if they encompass too many mutations, finally they are not, cannot proliferate. When the vaccine was introduced, that was a very bad day for the viruses.